It begins with a mystery that stretches back to the dawn of human curiosity, the question of what lies beneath everything we see. From the ancient philosophers who imagined matter as continuous, to those who believed in tiny, indivisible particles called atoms, humanity's journey to understand the fundamental nature of reality has been one of both imagination and evidence. Yet, the true revolution of atomic thought was not born from simple curiosity. It was born from the struggle between what we could see and what we could only believe. The world as we know it today, built on technology, energy, and quantum discovery, stands on the shoulders of that revolution. In the early days of science, atoms were more of an idea than a proven fact. The Greeks, like Democritus and Leucippus, proposed that everything was made of small, invisible, indestructible pieces. It was a beautiful theory, but without proof. For centuries, this vision slept in the shadows of philosophy, waiting for an age that could bring it to life through experiment and mathematics. When chemistry and physics began to rise in the 17th and 18th centuries, the idea re-emerged, but in a new form. Scientists such as John Dalton began to quantify matter, describing atoms not as mystical entities, but as measurable units of substance. Dalton's atomic theory was simple. Elements were made of identical atoms, and chemical reactions were rearrangements of these tiny units. It was the beginning of scientific atomism, but still, the atom was seen as solid, indivisible, and static, a tiny billiard ball that could not be broken down further. For much of the 19th century, this model held strong. It explained chemical reactions, it matched observations, and it gave structure to the periodic table. But as science pushed deeper, the cracks began to show. The discovery of the electron by J.J. Thomson in 1897 shattered the idea of the atom as an indivisible whole. The atom, it turned out, had parts, charged components, internal structure, and motion. The billiard ball had exploded into a miniature universe. It was the first true sign that the revolution had begun. Thomson's plum pudding model tried to explain this new world, a sphere of positive charge dotted with negative electrons like raisins in a pudding. But soon after, Ernest Rutherford's gold foil experiment in 1911 struck a fatal blow to that idea. When alpha particles were fired at thin gold foil, most passed through, but some bounced back sharply. It was as if bullets had ricocheted off invisible walls. The result was astonishing. The atom was mostly empty space, with nearly all its mass concentrated in a tiny, dense nucleus. It was a revelation that changed everything. The universe was not solid. It was a vast sea of emptiness, punctuated by flashes of energy and charge. This was the first true revolution of atomic thought, the realization that reality was not what it seemed. The atom, once imagined as a solid block, was now a dynamic structure with movement, energy, and internal forces. But even this new model, the planetary atom, with electrons orbiting the nucleus like planets around the sun, would not survive long. Nature, it seemed, refused to be boxed into human simplicity. In 1913, Niels Bohr introduced a new twist to this story. Building on Rutherford's nuclear atom and Planck's quantum hypothesis, he proposed that electrons could only occupy certain allowed orbits and that they could jump between these orbits by absorbing or emitting energy in discrete amounts, quanta. This was a bold idea. It married classical motion with quantum restriction, and it explained why atoms emitted light in specific spectral lines. The atom had rhythm, rules, and quantized behavior. It was no longer a mechanical miniature of the solar system. It was something stranger, something more elegant. This was a turning point in physics. The Bohr model explained hydrogen beautifully, but it also hinted that the laws governing atomic behavior were unlike those governing the motion of planets or falling apples. The microcosm had its own logic, a logic that challenged centuries of Newtonian certainty. It was here that the revolution of atomic thought truly deepened, not just in structure, but in philosophy. The universe was no longer purely deterministic. It was now governed by probabilities, jumps, and hidden truths that could only be glimpsed through mathematics and experiment. What followed was an explosion of insight. Planck's quantum theory, Einstein's photoelectric effect, and the growing evidence from spectroscopy all converged toward one conclusion: energy and matter were not continuous but quantized. The boundaries between particles and waves began to blur. Light, once thought to be purely a wave, behaved like a particle. Electrons, once thought to be particles, exhibited wave-like interference patterns. The revolution of atomic thought became a revolution of reality itself, a rewriting of what it meant to exist. Physicists around the world grappled with this new vision. Schrödinger introduced his wave equation, showing that electrons could be described as standing waves around the nucleus and that their energies corresponded to specific quantum states. Werner Heisenberg, in parallel, developed matrix mechanics, a mathematical approach that dispensed with visualization entirely and focused on measurable quantities. Both men had found different languages for the same truth. The atom was not a miniature solar system but a probability cloud, a world of uncertainty where observation shaped existence. And then came Heisenberg's uncertainty principle, a profound statement that one could never know both the position and momentum of a particle with perfect accuracy. This was not a limitation of instruments, it was a limitation of nature itself. Reality at its core was indeterminate. The revolution of atomic thought had turned the world upside down. Determinism, the foundation of classical science, had given way to probability. Certainty was gone, and in its place stood a deeper, humbler understanding of the universe. The philosophical shock of this transformation cannot be overstated. For centuries, scientists believed that if they knew all the laws of nature, they could predict the future of every object in the universe. But the new atomic reality defied this dream. Even if one knew everything about an atom, one could only predict the likelihood of where it might be, not where it was. The atom, in this sense, became both a physical object and a philosophical challenge, a reminder that knowledge itself had boundaries. The revolution was not just scientific, it was cultural. The new vision of the atom influenced art, literature, and philosophy. Writers and thinkers began to question the nature of certainty, identity, and observation. The idea that the observer could influence the observed resonated far beyond laboratories. In a way, the atom had become a mirror, reflecting not only the universe's secrets, but also humanity's thirst to understand them. Meanwhile, the practical side of this revolution began to emerge. As scientists learned to manipulate atomic energy and quantum effects, entire technologies were born. The structure of atoms explained chemistry at its most fundamental level. Understanding electron behavior led to the invention of transistors, lasers, and semiconductors, the foundation of the modern digital age. Nuclear physics, derived from atomic understanding, gave rise to both immense energy and immense danger. The power that once lived hidden inside matter was now in human hands. But before these technologies could shape the modern world, the revolution had to overcome one final barrier: the human tendency to cling to old ways of seeing. Many physicists of the early 20th century struggled to accept the idea of uncertainty and quantum indeterminacy. Einstein himself, though a pioneer of the quantum idea, famously resisted its implications. God does not play dice, he declared, expressing his discomfort with a universe ruled by chance. Yet, experiments proved again and again that nature did play dice, though perhaps with a cosmic elegance beyond human comprehension. This tension, between intuition and evidence, between classical order and quantum chaos, defined the intellectual atmosphere of the 20th century. It was not just about the atom anymore, it was about truth itself. Scientists had learned that to understand the smallest parts of the universe, they had to abandon the comfort of absolute answers and embrace the poetry of probabilities. The revolution of atomic thought was therefore both an ending and a beginning, the end of the mechanical age and the birth of the quantum age. The more scientists looked, the stranger the atom became. Inside its nucleus were protons and neutrons, themselves made of quarks held together by gluons, particles that exchanged energy in ways even more abstract than the electron's orbit. Each layer of discovery revealed a deeper, more complex dance of matter and energy. The atom, once seen as the simplest building block of the universe, turned out to be a cathedral of mystery, vibrating with fields, forces, and fluctuations. This transformation of understanding was not just an intellectual exercise, it changed how humanity interacted with nature. Atomic theory evolved into quantum field theory, merging with relativity to explain everything from the behavior of particles to the birth of stars. The revolution had grown from the invisible atom to the cosmic scale, uniting the microcosm and the macrocosm under one grand, probabilistic framework. Through all this, the atom remained both the symbol and the substance of modern physics, a reminder that the smallest things can contain the greatest truths. Each discovery brought with it not just new knowledge, but new humility. The deeper scientists looked, the more they realized that the universe was not a clockwork machine, but a symphony of possibilities. The revolution of atomic thought was not merely about understanding the atom, it was about redefining what it means to understand anything at all. The revolution also brought forth a new kind of scientist, not just a discoverer but a dreamer. These were individuals who dared to question the deepest assumptions of reality. They saw beyond the equations and into the essence of existence. They understood that the atom was more than a structure. It was a story, the story of nature's creativity, chaos, and order intertwined. The atom became the canvas on which humanity painted its new vision of the cosmos. Every new insight deepened the mystery. Why does energy come in discrete quanta? How can a particle be in multiple places at once? What truly happens when an observation collapses a wave function? These questions remain as haunting today as they were a century ago. The revolution of atomic thought, though it began with discovery, continues through inquiry, an endless pursuit to see beyond what is visible. And yet, perhaps that is the most profound legacy of this revolution. It taught humanity to see differently, to see that reality is not always what it appears to be, to see that knowledge requires imagination, to see that even in the smallest fragments of matter, there exists a universe waiting to be understood. From Democritus to Dalton, from Rutherford to Bohr, from Heisenberg to Schrödinger, the story of the atom is the story of thought itself, an unfolding dialogue between certainty and doubt, simplicity and complexity, light and darkness. The revolution of atomic thought was not a single moment in time, but a transformation in human perception. It changed not only science, but the very meaning of reality. As the 20th century dawned, the atom stood revealed as both a particle and a paradox, a place where logic met mystery and where observation became creation. This understanding became the cornerstone of modern science, shaping everything from quantum computing to cosmology. The revolution had not only redefined matter, it had redefined humanity's place within the cosmos. The story continues, as scientists probe deeper into the subatomic realm, discovering particles that flicker in and out of existence, fields that vibrate across space-time, and forces that bind the universe together. Each new discovery echoes the same truth that started it all, that reality is richer, stranger, and more beautiful than anyone could have imagined. And so, the revolution of atomic thought stands as one of the greatest turning points in human history. It is the story of how a simple question, what is the atom, led to answers that changed everything. It is a story of vision, of courage, and of the endless human desire to understand the unseen. It reminds us that every breakthrough begins with a moment of doubt, a spark of imagination, and a mind brave enough to see the world differently. The atom, once invisible and unknown, became the key to unlocking the universe. It was no longer a mere speck of matter, but a gateway to the infinite, a symbol of how far human thought could reach. And in that transformation, science found not just knowledge, but wonder. The revolution of atomic thought did not stop with discovery. It evolved into a living force that shaped the destiny of science itself. What began as curiosity in dimly lit laboratories soon became the foundation upon which entire civilizations would build their progress. The deeper scientists peered into the atom, the more astonishing truths emerged, truths that blurred the lines between imagination and mathematics, between philosophy and experiment. By the early 20th century, the old picture of reality had dissolved completely. The atom was no longer a mechanical structure, obeying the same rules as apples falling from trees or planets circling the sun. Instead, it was a theater of probabilities, where energy pulsed in quanta, and observation decided outcomes. This new understanding demanded not only new theories, but new ways of thinking. The mind of humanity itself had to stretch to meet the strangeness of nature. The birth of quantum mechanics became the second heartbeat of the revolution. Schrödinger's wave equation provided a tool to predict how electrons behaved, but it also painted an eerie picture. Electrons did not exist as tiny dots circling a nucleus. They existed as waves of probability, as if they were both everywhere and nowhere at once, until measured. To the human mind trained in classical logic, this was madness. But the universe had its own logic, subtle and precise. When experiments proved these predictions true, disbelief gave way to wonder. At the same time, Heisenberg's matrix mechanics stripped away visual comfort. It was mathematics unbound from images, an abstract symphony of numbers that described the invisible perfectly, though no one could see what it described. In the clash between these two views, the wave and the matrix, science discovered that both were parts of one truth. The atom could be understood only through the union of contradictory ideas. It was a humbling realization that truth was not singular but layered, multifaceted, and often paradoxical. From this paradox grew the modern vision of the universe. The revolution that began inside the atom rippled outward to touch every branch of physics. The quantum principles that described electrons soon applied to photons, nuclei, and even entire fields of energy. It became clear that the universe itself was woven from quantum threads. Every star that burns, every chemical bond that forms, every spark of electricity in our nervous system follows the rhythm first revealed by studying the atom. Yet as the revolution deepened, so did its mysteries. If observation could change outcomes, what was the role of consciousness? Did the observer truly shape reality, or was the act of measurement merely another physical process? Great minds debated these questions with passion. Bohr argued that physics must confine itself to what can be observed, while Einstein refused to believe that the moon did not exist when no one was looking. Their debates became legendary, not mere academic quarrels, but profound dialogues about the nature of existence. Through them, science matured, learning that progress often lives in disagreement. Outside the laboratory, the world was changing. Wars raged, empires rose and fell, and amid that turmoil the atom became both a symbol of hope and a warning. The same understanding that revealed the beauty of nature's building blocks also uncovered its terrible power. When nuclear fission was achieved, the atom's hidden energy leapt into human hands. The explosion over Hiroshima marked not only a triumph of intellect, but also a tragedy of application. The revolution of atomic thought had reached its most extreme expression. Humanity could now unmake what nature had built over eons. In the aftermath, the scientific community faced a reckoning. The same minds that had dreamed of understanding the universe now grappled with moral questions larger than equations. Many physicists, including those who had worked on the bomb, turned toward peace, education, and exploration. They realized that knowledge carries responsibility, and that the true purpose of science is not destruction, but enlightenment. The atom had spoken, and its voice demanded humility. The revolution, however, did not end with remorse. It transformed into a quest for harmony. As the Cold War accelerated, atomic research shifted toward energy, medicine, and understanding the cosmos. Nuclear reactors generated light for cities. Radiotherapy saved countless lives. The same principles that had powered weapons now powered progress. Humanity had begun to see that the atom's story was not only about energy, but about transformation. The transformation of fear into knowledge, of danger into discovery. At the same time, theoretical physics pushed the revolution into deeper realms. Quantum electrodynamics united light and matter in a single elegant theory, predicting experimental results with astonishing accuracy. Later, quantum chromodynamics revealed that even protons and neutrons were not fundamental, but composed of quarks dancing in fields of color charge. The atom, once considered the smallest unit of existence, became a gateway to a universe of subatomic symphonies. Each discovery peeled back another layer of reality, revealing beauty beyond imagination. Parallel to these developments, another frontier emerged, the quantum vacuum, a realm once thought empty but now known to be filled with flickering energy, virtual particles appearing and vanishing in an eternal dance. Space itself was no longer a silent void. It was alive, restless, creative. The revolution of atomic thought had expanded to fill the cosmos. Every star, every particle, every vibration in space-time whispered the same truth: existence is motion, fluctuation, and interconnection. This vision changed not only science but human consciousness. Philosophers, poets, and artists found inspiration in the quantum world. The atom became a metaphor for possibility, for the unseen forces shaping our lives. The uncertainty principle found echoes in psychology and art, where ambiguity and duality became sources of strength rather than confusion. The scientific revolution had sparked a cultural one, a realization that mystery and knowledge are not enemies but companions in the human journey. Meanwhile, new generations of scientists carried the torch forward. Quantum mechanics merged with Einstein's relativity in the search for a grand unified theory. From this effort emerged quantum field theory, then string theory, and the bold idea that the universe might consist of multiple dimensions, vibrating strings, and hidden symmetries. Each theory was an attempt to weave the atom's small-scale revolution into the fabric of the cosmos. Even now, experiments at particle accelerators probe deeper, smashing atoms to glimpse the secrets of creation. Through these explorations, one theme remains constant: the more we know, the more we realize how much remains unknown. The revolution of atomic thought is endless, precisely because it challenges the boundaries of certainty. Every measurement, every equation, every glimpse of the subatomic world reminds us that reality is a living question, not a fixed answer. And perhaps that is why it continues to captivate the human spirit, because it mirrors our own search for meaning. In classrooms around the world, children learn that everything is made of atoms, yet few pause to feel the weight of that truth. To know that every breath, every drop of water, every flicker of light is the result of atomic interactions is to glimpse the profound unity of existence. The revolution that began in the minds of a few scientists has now entered the consciousness of humanity. It has reshaped how we see ourselves, not as separate from nature, but as expressions of the same atomic tapestry. Technology, too, continues to echo this transformation. Quantum mechanics, once an abstract curiosity, now powers lasers, semiconductors, and the Internet. Quantum computers, still in their infancy, promise to revolutionize computation by exploiting the superpositions that once baffled the pioneers. The atom has not finished changing the world. It is only beginning. Each advancement traces its lineage back to that moment when someone first dared to see the atom differently. And yet, amid the progress, the philosophical core of the revolution endures. The atom teaches that certainty is an illusion, that the universe thrives on duality, light and darkness, order and chaos, particle and wave. It teaches that knowledge is not a destination but a journey, one that demands curiosity, patience, and humility. The more deeply we study matter, the more we encounter mystery, until science and spirituality meet at the same horizon of awe. Consider the atom as a metaphor for human understanding itself. Within its nucleus lies immense energy, locked away until the right questions unlock it. Around it swirl electrons, unpredictable, yet bound by laws. Observation reveals one aspect but hides another. The human mind operates in much the same way, filled with potential, surrounded by uncertainty, constantly transformed by awareness. In this sense, the revolution of atomic thought is also a revolution of self-understanding. As the 21st century unfolds, new instruments allow us to manipulate atoms one by one. Scientists build materials atom by atom, craft quantum bits that store information in delicate superpositions, and even simulate miniature universes inside computers. The frontier of physics has become the frontier of creativity. What once was theory has become craft. Humanity now shapes the very building blocks that once seemed untouchable. The revolution has come full circle, from observing atoms to engineering them. Yet, as always, progress carries responsibility. The same principles that enable miracles can also cause harm if wielded without wisdom. The atomic age taught this lesson brutally, and it remains as urgent as ever. The challenge of the future is not merely to know the atom, but to coexist with its power ethically. Science must continue to serve life, not threaten it. The revolution of thought must evolve into a revolution of conscience. In reflecting upon the journey of atomic discovery, one sees a pattern common to all human advancement: doubt leading to insight, insight leading to power, and power demanding wisdom. Each generation inherits both the knowledge and the questions of those before it. The atom, in its silent brilliance, reminds us that knowledge without wonder is hollow, and wonder without responsibility is dangerous. True understanding requires both. The revolution of atomic thought endures because it captures the essence of human inquiry. It tells us that even the smallest object can contain infinite depth, that the invisible governs the visible, and that every discovery opens more mysteries than it resolves. It transforms the act of seeing into the art of understanding, a continuous dialogue between the universe and the mind that seeks to comprehend it. In the end, the atom is not merely a particle of matter. It is a poem written by the universe in the language of energy. Its rhythms pulse through every heartbeat, its patterns shape every form, its quantum whispers echo in the galaxies above. To study it is to listen to the oldest music of creation. The revolution that revealed it did more than change science. It changed the story of what it means to be human. As the camera of imagination pulls back from the subatomic realm, we see that the same principles guiding the dance of electrons govern the birth of stars and the flow of time. The universe is one vast continuum of quantum processes, and we, conscious, questioning beings, are part of that process. The revolution of atomic thought invites us not only to understand the world, but to feel our place within it. So the story comes full circle. From the ancient philosophers who dreamed of indivisible particles to the modern scientists exploring quantum entanglement, the search has always been the same: to pierce the veil of the visible and find the truth that lies beneath. Each generation adds a verse to that eternal story. And while we may never reach the final answer, the pursuit itself is what defines us. The revolution of atomic thought endures in every experiment, every telescope, every equation scribbled in hope. It lives in the spark of curiosity that drives a student to ask why. It lives in the quiet dedication of scientists who chase mysteries through the night. It lives in the recognition that to know the atom is to know ourselves, fragile, uncertain, and yet infinitely powerful in our capacity to imagine. And so the revolution continues. It whispers through laboratories and classrooms, through the circuitry of computers and the depths of stars. It reminds us that reality is more than matter and motion. It is meaning in motion. The atom, once unseen and unknown, has become the storyteller of existence, and through it, humanity has learned that every question, no matter how small, holds the power to change the world forever. For centuries, the laws of nature seemed perfectly clear. The universe was a grand machine, ticking with flawless precision. Every planet followed its orbit, every pendulum swung with predictable rhythm, every object obeyed the same invisible rules. It was a world built on certainty, and that certainty was the triumph of classical physics. The legacy of Isaac Newton had defined the way humanity saw reality itself. The apple fell, the planets moved, and the equations matched perfectly. Nature was a book written in mathematics, and for nearly 300 years, those equations explained everything that could be seen, touched, or measured. But beneath the surface of that elegant order, a storm was waiting to be born, a challenge so profound it would shatter everything scientists thought they knew. By the late 19th century, physics stood as a completed cathedral of knowledge. Many believed that the great discoveries were over, that all that remained was to refine measurements and add a few missing details. Lord Kelvin himself declared that physics was almost complete, save for 2 small clouds on the horizon. But those 2 small clouds would soon unleash a tempest that would tear the foundations of classical thought apart. The first was the mystery of blackbody radiation, the strange way in which objects emit light when heated. The second was the behavior of light itself, sometimes acting as a wave, sometimes as if it were made of particles. These puzzles seemed minor at first, but they were cracks in the wall of classical certainty, and through those cracks a new universe would emerge. At the heart of classical physics was the belief in continuity. Energy, matter, and motion were smooth and predictable, capable of infinite division. A moving object could have any speed, any energy, any trajectory, as long as it obeyed Newton's laws. But in 1900, a quiet German physicist named Max Planck dared to suggest something that sounded impossible, that energy did not flow smoothly, but in tiny, discrete packets called quanta. He made this suggestion only to solve a stubborn problem about the spectrum of light emitted by hot objects, but what he discovered was far more profound. The idea that energy comes in indivisible quanta was like a thunderclap across the scientific world. Planck himself resisted the implications of his own discovery. He was a man of classical training, and to him, the quantum hypothesis was a mathematical trick, not a revolution. But nature had already spoken. The equations worked perfectly, the only ones that could explain reality where all others failed. A few years later, Albert Einstein extended Planck's idea to explain the photoelectric effect, showing that light itself behaves not as a continuous wave, but as particles, photons, that carry discrete amounts of energy. In that moment, the second cloud on Kelvin's horizon erupted into lightning. The elegant wave theory of light, cherished since the days of Huygens and Maxwell, now stood in conflict with the new particle theory. How could light be both? This contradiction was unbearable to classical minds. The principles that had guided generations, determinism, continuity, causality, were under siege. The world that had once seemed mechanical and knowable now flickered with uncertainty. Classical physics had given humanity the confidence that every effect had a cause, and every motion could be predicted if one only knew the forces at play. But as scientists began to peer deeper into the structure of matter, they found that the rules changed in the small world. The atom, once thought indivisible, had an inner structure. Electrons orbited nuclei, charges interacted through invisible fields. Yet even these orbits did not behave as expected. Electrons should have spiraled into the nucleus according to classical electromagnetism, but somehow they did not. They existed in stable states that classical theory could not explain. When Niels Bohr entered the scene, he attempted to rescue the atom from classical collapse. His model introduced quantized orbits, energy levels that electrons could occupy without radiating energy, and discrete jumps between them when absorbing or emitting light. It was a bridge between the old world and the new, a fragile truce between continuity and quantization. For a moment it seemed to work. The hydrogen atom spectrum matched perfectly. But Bohr's model was only a patch, not a solution. Beneath its success, the conflict between classical and quantum thinking grew sharper. The challenge to classical physics was no longer a question of numbers. It was a question of meaning. What did it mean for energy to be quantized? What did it mean for light to behave as both wave and particle? The answers that once came easily from Newton's laws now dissolved into paradox. The universe was no longer a clockwork of gears and motion, but a tapestry of probabilities and dualities. The familiar ground of cause and effect began to tremble beneath the feet of scientists who had built their careers on certainty. To understand how deep the challenge ran, one must step into the mind of a physicist in 1910. Imagine a world where every observation fits neatly into a framework that has worked flawlessly for centuries. And then, suddenly, experiments begin to defy those laws. The photoelectric effect refuses to obey the predictions of wave theory. Blackbody radiation behaves in ways that continuous equations cannot explain. The orbiting electron, by all logic, should collapse into the nucleus in a fraction of a second, yet it does not. The old equations, once so perfect, now fail to describe the smallest pieces of matter. It was not just confusion, it was betrayal. Nature had broken her own rules. The challenge to classical physics was not a single event, but a gradual unraveling. One by one, the pillars that held up the Newtonian universe began to fall. First, the assumption of determinism, that knowing the present allowed prediction of the future, began to crumble under quantum uncertainty. Then, the belief in continuity, that all quantities could vary smoothly, gave way to the discovery of discrete energy levels and indivisible quanta. Even the separation between particle and wave, matter and energy, began to blur. Einstein's own equation, E equal to mc2, revealed that mass and energy were not separate entities at all, but two sides of the same coin. The classical world had dissolved into a shimmering unity where distinctions lost meaning. For the scientists who lived through this period, the experience was both exhilarating and terrifying. The comfort of certainty was gone, replaced by the beauty of mystery. They were explorers in a land without maps, forced to invent new mathematics, new concepts, even new language to describe what they found. Heisenberg, Schrödinger, de Broglie, and Dirac each took up the challenge in their own way. De Broglie proposed that matter, like light, had wave properties, that electrons could behave as both particles and waves. Schrödinger took that idea and crafted his wave equation, a masterpiece that described how electrons exist not in orbits, but in clouds of probability. Meanwhile, Heisenberg built an entirely new framework, matrix mechanics, that ignored the unobservable and focused only on measurable quantities. To the classical physicist, this was chaos. To the quantum pioneers, it was the birth of a new order. The challenge to classical physics had forced them to abandon the old picture of reality, but in doing so, they discovered a deeper one, a reality governed not by certainty, but by possibility. This philosophical shift was monumental. In the classical world, the universe was passive, predictable, indifferent to observation. But in the quantum world, observation itself became part of the story. The act of measuring an electron's position changed its momentum. The act of watching changed what was watched. Reality had become participatory, elastic, alive. The notion that human awareness could influence the outcome of an experiment was so radical that even Einstein refused to accept it. To him, the moon must exist whether anyone looked at it or not, but the new physics whispered otherwise. At the deepest level, existence itself seemed tied to interaction. For many, this was more than a scientific challenge. It was an existential one. The dream of a perfectly predictable universe had died. Humanity had stepped into a cosmos where certainty was replaced by probability, where knowledge meant embracing limits. Yet, in that uncertainty, lay profound beauty. The challenge to classical physics was not merely the destruction of an old worldview, it was the awakening of a new one. In this new world, electrons did not orbit neatly like planets. They vibrated in standing waves, forming patterns that resembled music more than machinery. Atoms, once seen as hard spheres, became dynamic fields of energy. Light, once a wave, was also a particle, and sometimes both at once. Nature, it seemed, spoke in poetry, not in prose. But poetry demands interpretation, and the physicists of the early 20th century became reluctant poets of the invisible. They struggled to find meaning in their own equations, to reconcile their intuitions with a universe that refused to be pinned down. The challenge to classical physics was as much a challenge to the human mind as it was to mathematics. It required a new way of seeing, one that accepted paradox as truth and uncertainty as law. This revolution did not come quietly. It came with debate, resistance, and sleepless nights spent over chalkboards filled with symbols that hinted at a reality no one could picture. Schrödinger himself felt haunted by his own wave equation, wondering what it truly described. Heisenberg, seeking clarity, found only deeper uncertainty. Einstein, who had helped ignite the quantum revolution, grew increasingly uneasy with its implications. God does not play dice, he said, rejecting the randomness at the heart of quantum mechanics, to which Niels Bohr replied with calm conviction, "Stop telling God what to do." The dialogue between these giants was more than intellectual sparring. It was the voice of science wrestling with its soul. The classical dream of total predictability had ended, but in its place came a richer, more mysterious vision of the universe, one that invited endless discovery. The challenge to classical physics, once seen as a crisis, became a catalyst. It pushed humanity beyond the boundaries of certainty and into the infinite frontier of imagination. As the first decades of the 20th century unfolded, The results of this challenge became visible everywhere. Quantum theory explained why the sun shines, why metals glow, why chemistry behaves as it does. It laid the foundation for modern electronics, for lasers, for semiconductors, for nuclear energy. Every technology that defines the modern world, from the light in your room to the chip in your computer, is a child of that challenge. Yet, for all its triumphs, the new physics did not replace the old completely. Classical physics still ruled the macroscopic world, the motion of planets, the flight of airplanes, the mechanics of bridges. But deep beneath those visible systems, the quantum world pulsed, silent and strange, shaping everything. The two worlds coexisted, divided not by contradiction but by scale. The challenge, it turned out, was not to destroy classical physics, but to understand its limits, and beyond those limits, to find the deeper harmony of nature. By the time the quantum revolution had settled, the meaning of reality itself had changed. The universe was no longer a predictable machine, but a living equation, a sea of potential that collapsed into form only when observed. The challenge to classical physics had revealed a profound truth. Certainty was an illusion, but understanding could still thrive within uncertainty. In embracing that paradox, science had grown wiser and more human. The journey was far from over. New questions were rising about relativity, about space-time, about the very fabric of the cosmos. But the challenge to classical physics had already achieved its greatest victory. It had taught humanity that knowledge is not about control, but about wonder, that to understand the universe, one must first learn to listen to its silence, and that sometimes the most beautiful truths are the ones that refuse to be simple. As the 20th century progressed, the implications of the challenge to classical physics became ever more profound. What began as a few inexplicable experimental results had grown into a complete reimagining of the universe. The certainties of the Newtonian era, once considered eternal, now appeared as approximations valid only within limits of scale and energy. At the atomic and subatomic level, these approximations shattered, revealing a cosmos far stranger and more intricate than anyone had imagined. The pioneers of this new era of physics found themselves in a landscape of paradoxes, where observation and existence, probability and reality, seemed inseparably entwined. Consider the electron, once conceived as a tiny particle orbiting the nucleus like a planet around the sun. In the new quantum world, electrons no longer traveled along defined paths. They existed as clouds of probability, patterns of potentiality that could only be described mathematically. Schrödinger's wave equation captured this reality, showing that the electron's position and momentum could never be known simultaneously with perfect accuracy, a revelation codified by Heisenberg in his uncertainty principle. Classical physics, with its assumptions of continuity and determinism, had no tools to grapple with this reality. Yet for those who embraced it, the atomic world became a vast, intricate dance, a choreography of probabilities that spoke of elegance and order hidden within apparent chaos. This new understanding of matter also redefined the concept of energy. Energy was no longer a smooth river flowing endlessly. It came in discrete quanta, stepping down like the rungs of an invisible ladder. Light, once understood purely as a wave, could act as a stream of particles, photons, delivering energy in exact packets. This dual nature of light, at once wave and particle, defied the classical dichotomies that had shaped centuries of thought. It required an entirely new logic, one that did not reject the old laws but placed them within a broader, more intricate framework. The challenge to classical physics was not merely technical, it was deeply philosophical. Newtonian mechanics had promised predictability, a universe that could be mapped and known in its entirety. Quantum mechanics revealed that this promise was limited. At the microscopic scale, reality became fundamentally uncertain. Deterministic equations could no longer predict individual outcomes, they could only assign probabilities. Scientists, once comfortable with the notion that knowledge equaled certainty, now had to reconcile with the idea that the universe possesses an intrinsic unpredictability. This intellectual upheaval was felt personally by the leading physicists of the era. Einstein, who had catalyzed the quantum revolution through his work on the photoelectric effect, remained skeptical of its philosophical implications. He famously remarked that God does not play dice with the universe, expressing his discomfort with the probabilistic nature of quantum mechanics. Bohr, in contrast, embraced the implications, arguing that the limits of measurement were not failures of human intellect, but intrinsic properties of nature itself. The tension between these perspectives fueled debates that were both technical and existential, shaping the course of scientific thought for decades. The challenge to classical physics also reshaped experimental practice. Precision measurements, once tools for confirming existing theories, became instruments for discovering new ones. Laboratories across Europe and America were transformed into theaters of uncertainty, where the most delicate instruments captured flashes of particles, interference patterns, and quantum jumps. Every experiment, no matter how controlled, revealed a world that refused to conform to classical expectations. The more closely scientists looked, the stranger reality became, compelling them to develop ever more sophisticated tools and techniques to probe the invisible. This struggle to reconcile observation with theory produced some of the greatest triumphs of modern physics. Quantum mechanics explained phenomena that classical physics could not touch: the stability of atoms, the emission spectra of elements, the behavior of electrons and metals, the mysterious interactions of light and matter. The predictions were not just accurate, they were astonishingly precise, verified to an accuracy unimaginable a century earlier. Nature, once thought to be fully comprehensible, proved both obedient and inscrutable. Classical physics remained an approximation of the macroscopic world, but quantum mechanics opened a window into the foundational principles of existence. Yet the revolution was not confined to the laboratories. Its philosophical and cultural ramifications spread quickly. Writers, artists, and thinkers grappled with a universe where certainty was provisional, where reality depended on perspective and observation. The classical worldview, which had inspired the Enlightenment and the Industrial Revolution, now seemed incomplete. If matter itself defied intuitive logic, what could be assumed about the broader cosmos? The atom, once invisible and inert, became a symbol of a universe more intricate, mysterious, and interconnected than previously imagined. The implications extended into technology as well. The understanding of quantum behavior laid the groundwork for semiconductors, transistors, and ultimately the digital revolution. Lasers, magnetic resonance imaging, and solar cells all trace their origins to the insights that challenged classical physics. Without embracing the counterintuitive principles of the quantum world, modern civilization would look entirely different. Every piece of advanced technology today, every microchip, every fiber optic cable, every piece of medical imaging equipment exists because the classical worldview was questioned and reshaped. In this period, the atom became both a laboratory and a lens through which to explore deeper truths. Each experiment revealed patterns, symmetries, and consistencies that classical mechanics could not predict. At the same time, each discovery highlighted the limitations of human intuition. Electrons exhibited interference patterns when unobserved, yet behaved like particles when measured. Light exhibited the same duality, wave and particle, intertwined in ways that defied logic but matched experiment perfectly. The classical categories, solid and fluid, wave and particle, cause and effect, were revealed to be approximations useful for large-scale phenomena but incomplete at the foundational level. The challenge to classical physics was also a challenge to imagination. For centuries, humans had visualized the universe as a clockwork mechanism, predictable and comprehensible. Quantum mechanics demanded new visualizations, abstract and mathematical, often incomprehensible to the mind's eye. Physicists learned to think not in pictures but in probabilities, in wave functions, in operators and matrices. They learned to embrace paradox, to accept that opposites, particle and wave, certainty and uncertainty, could coexist as aspects of a deeper truth. The universe became less a machine than a symphony, a complex composition whose notes were probabilities rather than certainties. This conceptual shift demanded courage. The very tools of reasoning that had guided scientific progress now seemed insufficient. to embrace the quantum worldview was to acknowledge the limits of human perception and intuition. It was to accept that reality could operate according to rules that seemed absurd when compared to everyday experience. And yet, in embracing these limitations, scientists discovered a freedom, the freedom to describe the universe in richer, more accurate ways, unbound by the constraints of classical expectation. The process of overcoming these challenges was gradual and iterative. Early attempts to reconcile quantum phenomena with classical mechanics often failed. Bohr's quantized orbits were a temporary solution. Einstein's objections highlighted unresolved paradoxes. Only through decades of intense work, collaboration, and debate did a coherent framework emerge. Schrödinger's wave mechanics, Heisenberg's matrix mechanics, and Dirac's relativistic formulations converged into a consistent theory capable of describing a vast range of phenomena. The challenge, it turned out, was not merely technical but conceptual, to reconceptualize reality itself. As quantum mechanics matured, the boundaries between classical and modern physics became clearer. Classical physics remained immensely useful for macroscopic phenomena, rockets, bridges, planets, tides, and machines. But at the microscopic scale, classical predictions failed. Electrons, photons, and atomic nuclei obeyed laws that required probabilistic, not deterministic descriptions. The challenge to classical physics had thus reshaped the hierarchy of scientific understanding, classical mechanics as an approximation, quantum mechanics as the fundamental framework. The revolution also changed how humans understood causality. In the classical worldview, every effect had a predictable cause. Given enough information, the future could be calculated precisely. Quantum mechanics revealed a different form of causality, one where probability distributions replaced certainty, where outcomes could only be predicted statistically. This was not a failure of science but an expansion of understanding, acknowledging the subtle and hidden structures that govern the behavior of matter. By mid-century, the challenge to classical physics had produced a complete paradigm shift. Physics was no longer a study of predictable machines, but an exploration of potentialities. Atoms were not billiard balls, they were dynamic systems governed by probabilities. Light was not a simple wave, it was a dual entity, wave and particle intertwined. Energy was not continuous, it was quantized. Classical intuition, while still valuable for everyday life, could no longer serve as a guide to fundamental phenomena. The very meaning of understanding had changed. This shift also rippled beyond science. Philosophers debated the implications for determinism, free will, and the nature of reality. Artists and writers found inspiration in ambiguity, duality, and uncertainty. The challenge to classical physics had opened a window not just on the atomic world, but on the human imagination. It taught that reality is more subtle than perception, more intricate than expectation, and more beautiful than simple certainty allows. Even today, the legacy of this challenge endures. The technologies, experiments, and theories it produced form the backbone of modern physics. Quantum mechanics drives innovations in computing, communication, medicine, and energy. Yet the conceptual revolution remains as profound as ever. It continues to influence how we think about knowledge, observation, and the limits of human comprehension. Classical physics, once seen as the final word, is now understood as a chapter in a larger ongoing story. A story that began when nature refused to be simplified and demanded that humans see differently. The challenge to classical physics thus stands as one of the most transformative episodes in the history of science. It was not merely a correction of equations or a refinement of theory. It was a reimagining of reality itself. It forced humanity to confront the limitations of intuition, the necessity of probability, and the subtle interplay between observation and existence. In this way, the challenge did more than change physics. It changed the very lens through which humans perceive the cosmos, teaching that even the most reliable laws have their domain, and beyond that domain, mystery reigns. The story of this challenge is also a story of courage. Courage to question assumptions long held sacred. Courage to confront paradoxes that defied comprehension. Courage to trust mathematics and experiment over intuition. Every equation scribbled on a blackboard, every experiment painstakingly conducted, every debate carried out in the lecture halls and correspondence of the era, represents a step into the unknown. The challenge to classical physics was a call to intellectual bravery, a reminder that progress often requires abandoning certainty to find deeper truth. In contemplating this period, one realizes that the challenge to classical physics was not just a scientific endeavor, but a human one. It involved creativity, imagination, doubt, and persistence. It revealed that understanding reality is not a linear process, but a journey of discovery, often through contradiction and paradox. The classical worldview, elegant as it was, could not encompass the richness of the atomic and subatomic worlds. To embrace the challenge was to embrace a larger vision, one in which simplicity coexists with complexity, determinism with probability, and perception with mystery. At the dawn of the 20th century, the seeds of a new era in physics had been sown. The limitations of classical mechanics, once thought absolute, had become undeniable. Experiments had exposed cracks in the foundations, revealing a universe that defied intuition and demanded a radical new way of thinking. Scientists were no longer content with mere observation of phenomena. They sought a comprehensive framework, a language capable of describing the invisible, the fleeting, the probabilistic. It was into this restless climate of curiosity and uncertainty that quantum mechanics emerged, not as a single discovery, but as a revolution, unfolding step by step, idea by idea, equation by equation. Max Planck, whose work on blackbody radiation had first hinted at quantization, stood at the origin of this transformation. His insight was deceptively simple. Energy could not be divided infinitely, it came in discrete packets. He called them quanta, and although he considered this a mathematical expedient, it proved to be the first glimmer of a new paradigm. Suddenly, the smooth, continuous flow of energy envisioned by classical physics was replaced by an elegant staircase of possibility. The implication was enormous. It meant that the universe at its most fundamental level was granular, structured, and yet governed by precise rules. Rules that were invisible to the senses, but readable through mathematics. Albert Einstein took Planck's revolutionary concept further. In 1905, he applied the quantum hypothesis to light itself, demonstrating that photons, packets of light energy, could explain the photoelectric effect, a phenomenon that had defied classical explanation for decades. For the first time, light was understood as a particle, yet it retained its wave-like properties in other contexts. This duality seemed paradoxical, a contradiction in terms, yet it fit the experimental evidence perfectly. It signaled a universe that was not simply what it appeared to be, but something richer, more nuanced, and far stranger than previously imagined. Meanwhile, Niels Bohr turned his attention to the atom itself. Classical physics predicted that electrons orbiting a nucleus should radiate energy and spiral inward, collapsing the atom in an instant. Yet atoms were stable, and their spectral lines were discrete and precise. Bohr introduced a bold idea. Electrons could occupy only certain energy levels, and when they jumped between them, they absorbed or emitted energy as quanta. His model was a bridge, a compromise between the familiar classical ideas and the emerging quantum logic. It worked with astonishing accuracy for hydrogen, explaining its spectral lines and opening a window into the inner workings of the atom. Yet Bohr's model was not complete. It was a stepping stone, a hint of a deeper structure waiting to be revealed. Louis de Broglie, inspired by the wave-particle duality of light, proposed that matter itself exhibited similar properties. Electrons were not mere particles orbiting nuclei, they also behaved like waves, capable of interference and diffraction. This radical idea suggested that matter, like energy, had dual aspects, challenging the traditional distinction between solid particles and waves. It implied that the classical notion of a localized particle was incomplete, that beneath the surface of reality lay patterns of probability and oscillation, a rhythm of existence both beautiful and counterintuitive. The formulation of Schrödinger's wave equation in 1926 marked a turning point. The equation described how the wave-like properties of electrons evolved over time, predicting the probability distributions for their locations around the nucleus. Electrons were no longer pinpointed bodies but diffuse clouds, their positions defined only statistically. Schrödinger's work transformed the atom from a simple mechanical model into a dynamic, probabilistic system. It was as if the invisible threads of the universe had been revealed, showing the underlying structures that guided the dance of particles. At the same time, Werner Heisenberg developed matrix mechanics, a different but complementary formulation of quantum mechanics. Instead of focusing on wave functions, Heisenberg considered observable quantities and their relationships, emphasizing what could be measured rather than what could be imagined. His approach led directly to the uncertainty principle, the realization that certain pairs of physical properties, such as position and momentum, could never be precisely known simultaneously. Observation itself influenced reality. The universe was no longer a passive stage, but a participatory process, in which measurement was inseparable from the phenomena observed. Quantum mechanics, in its full form, shattered classical notions of determinism and continuity. It revealed a universe governed by probabilities, where outcomes were not predetermined but influenced by chance and context. Yet this was not chaos, it was a new kind of order, subtle, intricate, and profoundly elegant. Mathematical structures, once considered abstract and detached from reality, became the most accurate guide to nature's behavior. The rules of the subatomic world were precise, consistent, and predictive, even when they defied human intuition. The dawn of quantum mechanics was also a human story, filled with debates, doubts, and triumphs. Einstein, who had catalyzed much of the early work, struggled with the probabilistic nature of the theory, famously declaring that God does not play dice with the universe. Niels Bohr, conversely, embraced the uncertainty, arguing that physical reality could only be described in terms of observable phenomena. Their exchanges, conducted in letters and at the Solvay conferences, were more than technical disputes. They were philosophical dialogues about the nature of existence itself. The tension between determinism and probability, intuition and evidence, classical and quantum, shaped the development of the theory and inspired generations of scientists to explore the unknown. The implications of quantum mechanics extended beyond atoms. Nuclear physics, solid-state physics, and chemistry all found their foundations in these principles. The behavior of electrons in atoms explained chemical bonds, the formation of molecules, and the properties of materials. Understanding quanta allowed scientists to predict and manipulate phenomena that had been mysterious for centuries. Technologies that define modern life, semiconductors, lasers, transistors, magnetic resonance imaging, all trace their roots to the early quantum discoveries. The dawn of quantum mechanics was not just theoretical, it was practical, transforming the material world and opening possibilities previously inconceivable. At the same time, the theory revealed new paradoxes that challenged perception. Schrödinger's famous thought experiment, the cat simultaneously alive and dead, illustrated the counterintuitive nature of superposition, a system existing in multiple states until observed. Entanglement, where particles became mysteriously connected across distance, suggested that reality was interconnected in ways that classical physics could not explain. These concepts were unsettling, yet they revealed deeper truths about the universe, prompting a reevaluation of causality, locality, and the nature of reality itself. The dawn of quantum mechanics was also a story of synthesis. Wave mechanics and matrix mechanics, initially seen as competing approaches, were shown to be mathematically equivalent, two languages describing the same phenomena. Dirac's formalism unified these approaches further and introduced the concept of quantum fields, extending the theory to encompass a wider range of particles and interactions. The work of countless scientists, from Bohr and Heisenberg to Dirac and Pauli, converged into a coherent framework capable of explaining and predicting phenomena at the smallest scales. The human element of this revolution cannot be overstated. The early pioneers worked under conditions of uncertainty, intellectual tension, and personal struggle. They had to abandon intuitions that had guided centuries of thinking and embrace a worldview that was both abstract and alien to everyday experience. Their courage lay not only in mathematical insight, but in the willingness to imagine a universe fundamentally different from the one they had been taught to believe in. The dawn of quantum mechanics demanded not only intellect but imagination, perseverance, and philosophical openness. This period also witnessed the rise of the quantum worldview beyond physics. Philosophers, artists, and writers were inspired by the notion that reality is not fixed, that observation shapes experience, and that uncertainty is intrinsic to existence. The implications of quantum mechanics resonated far beyond the laboratory, influencing how humans thought about knowledge, perception, and the limits of certainty. The dawn of quantum mechanics was therefore not just a scientific revolution but a cultural one, challenging assumptions about reality, causality, and the relationship between observer and observed. Experiments continued to probe the boundaries of this new theory. Particle accelerators, cloud chambers, and spectroscopy revealed phenomena that classical physics could not approach. The hydrogen atom's spectral lines were fully explained. Electron diffraction confirmed de Broglie's hypothesis. The quantization of energy levels in solids and atoms became essential knowledge. Each experiment reinforced the validity of the quantum framework, gradually winning over skeptics and solidifying a revolution that had begun with small, puzzling anomalies in classical predictions. At the same time, the theory revealed its predictive power. Quantum mechanics accurately described the behavior of semiconductors, superconductors, and lasers. It explained chemical bonding, catalysis, and the periodic table with unprecedented precision. The precision of quantum theory was breathtaking. Predictions matched experimental results to decimal points unimaginable in the classical era. The dawn of quantum mechanics had transformed physics from a descriptive science into one capable of predictive mastery at the atomic and subatomic scale. The philosophical implications were equally profound. Determinism, once the cornerstone of classical thought, was replaced by a probabilistic view. Reality became participatory, in which measurement and observation were integral to the unfolding of events. Superposition, entanglement, and uncertainty forced a re-evaluation of the very concept of reality, revealing a world where what is observed depends on how it is observed. The dawn of quantum mechanics, therefore, was not just about particles and waves, it was about the very nature of knowledge, existence, and the human role in perceiving the universe. In classrooms and laboratories, the ideas of the quantum revolution spread. Young physicists absorbed the principles of wave-particle duality, quantization, and uncertainty. Seminars and conferences buzzed with debates, experiments, and speculation. The dawn of quantum mechanics marked the birth of a new scientific culture, one that valued abstract reasoning, mathematical rigor, and openness to counterintuitive truths. It was a culture in which the imagination became as vital as observation, and where bold hypotheses could lead to profound insights into the structure of reality. The dawn of quantum mechanics was also a story of global collaboration and competition. Centers of research in Europe and the United States became crucibles of innovation, with scientists exchanging letters, publishing papers, and attending conferences to debate the implications of the new theory. The Solvay conferences, in particular, became legendary forums where the greatest minds of the era, Einstein, Bohr, Heisenberg, Schrödinger, Dirac, and Pauli, grappled with the implications of quantum mechanics. These meetings were more than technical discussions, they were intellectual dramas in which the fate of classical assumptions and the birth of a new worldview were contested and clarified. As the 1920s progressed, the abstract principles of quantum mechanics began to take concrete shape in the laboratory. Theoretical predictions were tested, measured, and confirmed with astonishing precision. Electron diffraction experiments verified de Broglie's proposal that matter could behave as a wave, revealing interference patterns that classical particles could never produce. Spectroscopy of atomic transitions consistently matched the predictions of Schrödinger's equations. The atom, once a mystery, became a landscape of quantized energy levels, dynamic wave functions, and probabilistic behavior. Yet the more accurately experiments confirmed the theory, the stranger reality seemed. Entanglement, a concept later formalized by Schrödinger, emerged as a phenomenon that defied classical intuition. Two particles, once interacting, could remain correlated across vast distances, so that measuring one instantaneously affected the state of the other. This spooky action at a distance, as Einstein called it, challenged not only the classical notion of locality, but also the very fabric of causality itself. The universe revealed an interconnectedness that classical physics could never accommodate, a web of relationships underlying all matter and energy. Scientists were forced to abandon the comforting notion that distant objects could be considered independent. The quantum world operated under laws both subtle and profoundly interdependent. During this time, the debates between the architects of quantum theory reached their most intense moments. Einstein, Bohr, Heisenberg, and Schrödinger often confronted one another at conferences and in correspondence, probing the philosophical implications as deeply as the technical ones. Einstein, with his insistence on determinism and realism, remained skeptical of probabilistic interpretations, challenging colleagues to reconcile theory with intuition. Bohr countered, emphasizing that the quantum world simply required a new understanding, that nature does not always conform to human preconceptions. These exchanges were not mere arguments, they were dialogues that reshaped the very way humanity conceives reality, forcing physicists to confront the limits of perception, logic, and certainty. Quantum mechanics also began to unify seemingly unrelated phenomena. The rules that governed the hydrogen atom extended to multi-electron atoms, explaining their chemical properties and bonding patterns. The periodic table, once empirical, found its theoretical foundation in quantum rules. Solid-state physics emerged as a discipline, using quantum principles to explain conductivity, semiconductivity, and magnetism. These insights were not abstract curiosities. They formed the basis for practical technologies that would transform society. Transistors, diodes, lasers, and eventually computers were direct descendants of the quantum revolution, a testament to the predictive and transformative power of theory when paired with experiment. The mathematical elegance of quantum mechanics was also striking. Wave functions, matrices, and operators describe systems with precision, even when classical intuition failed. Probability distributions replaced deterministic trajectories, and operators encoded the rules that governed observables. Schrödinger's formalism allowed the visualization of atomic orbitals as three-dimensional probability clouds, while Heisenberg's matrix mechanics provided an abstract framework to calculate observable quantities without specifying unmeasurable details. These complementary approaches highlighted the richness of the theory and its capacity to capture phenomena that classical physics could not approach. Yet for all its triumphs, quantum mechanics remained counterintuitive. Schrödinger's cat, a thought experiment conceived to illustrate superposition, underscored the conceptual challenges, a system existing in multiple states simultaneously until observation forces it into one. Entanglement further revealed that measurement affects reality instantaneously across distance, a challenge to classical ideas of separability and causality. The macroscopic world seemed stable and deterministic, but at the quantum scale, the universe was probabilistic, fluid, and interconnected in ways that defied imagination. Scientists had to cultivate new modes of thinking, learning to interpret mathematics as a guide to reality rather than as a mere tool for calculation. The implications for philosophy were profound. Classical determinism, which had dominated Western thought since Newton, gave way to a probabilistic understanding. Observation became inseparable from existence, suggesting that knowledge of reality is not simply a reflection of an external world, but a participatory act. Reality was no longer fixed, it was relational, dependent upon interaction and context. These ideas reverberated far beyond physics, influencing metaphysics, epistemology, and even literature and art. The dawn of quantum mechanics marked a paradigm shift in human thought, one that redefined certainty, objectivity, and the nature of existence itself. The experimental verification of quantum principles continued relentlessly. Spectroscopic analysis confirmed energy quantization in multiple elements. Electron diffraction revealed interference and wave-like behavior. The Stern-Gerlach experiment demonstrated quantized angular momentum, showing that spin, an intrinsic property of particles, took only discrete values. Each confirmation reinforced the robustness of the theory and expanded its explanatory power, transforming quantum mechanics from a speculative framework into the definitive description of the microscopic world. Dirac's contributions further expanded the scope of quantum mechanics. By incorporating relativity into the framework, he predicted the existence of antimatter, a concept later confirmed by the discovery of the positron. His elegant equations unified previously disconnected phenomena, revealing deep symmetries and suggesting that the universe's underlying structure was far richer than previously imagined. Quantum mechanics had moved beyond the atom. It now encompassed particles, fields, and the interactions that govern the cosmos itself. The dawn of quantum mechanics also transformed education and research. Universities established new programs focused on quantum theory, training a generation of physicists to think in terms of wave functions, operators, and probability distributions. Laboratories became centers of innovation, equipped with instruments capable of measuring phenomena at previously unimaginable scales. The culture of physics shifted. Experimentation and theory were intertwined in a dynamic dialogue, each informing and refining the other, producing a feedback loop that accelerated discovery. Technological applications multiplied. The understanding of semiconductors paved the way for the electronic revolution. Lasers, which rely on controlled quantum states, became essential tools in communication, medicine, and industry. Nuclear physics, grounded in quantum theory, led to both energy production and deeper understanding of fundamental forces. The abstract ideas first proposed by Planck, Einstein, and Bohr now manifested in tangible transformative technologies, demonstrating that even the most counterintuitive principles could have profound real-world impact. The conceptual richness of quantum mechanics also inspired new ways of thinking about reality. Superposition and entanglement suggested a universe that is fundamentally relational. Measurement, rather than passive observation, became an active engagement with the world. The deterministic universe of classical physics was replaced by a tapestry of probabilities, a reality in which certainty exists only as a limit within a broader, probabilistic structure. This new vision required humility, creativity, and a willingness to accept that the universe may operate according to principles far removed from everyday experience. The human stories within this revolution were compelling. Einstein's skepticism, Bohr's pragmatism, Heisenberg's precision, and Schrödinger's creativity exemplified the interplay of intellect, intuition, and courage. Their correspondence, debates, and experiments reveal a process of discovery that was as much philosophical and psychological as it was technical. The dawn of quantum mechanics was not only a scientific achievement, but a testament to human imagination, perseverance, and the relentless pursuit of understanding. By the 1930s, quantum mechanics had become a fully established framework, capable of describing atomic, subatomic, and molecular systems with remarkable accuracy. Predictions of atomic spectra, chemical bonding, and particle behavior aligned with experimental results. The theory provided not only explanations for existing phenomena, but also the ability to anticipate entirely new phenomena, demonstrating the predictive power that distinguishes successful scientific frameworks from mere speculation. At the same time, quantum mechanics revealed limitations in classical concepts. Position, momentum, energy, and spin were no longer absolute. They existed within probability distributions, constrained by uncertainty principles. Cause and effect retained meaning at macroscopic scales but required reinterpretation at microscopic scales. Space and time, once continuous and independent, were entwined with fields and quantum interactions. The dawn of quantum mechanics redefined the boundaries between classical and modern physics, providing a deeper understanding of both while highlighting the limits of human intuition. The theory also prompted broader reflections on the nature of knowledge. Scientific understanding was no longer merely about observation or measurement. It required the construction of abstract frameworks capable of describing phenomena beyond direct perception. Mathematics became a bridge between the visible and invisible, translating experimental data into coherent models of reality. Quantum mechanics demonstrated that understanding is not a passive reflection of the world, but an active engagement with its structures, patterns, and probabilities. As the applications of quantum mechanics expanded, so too did its influence on culture and philosophy. Concepts of uncertainty, duality, and superposition resonated with thinkers across disciplines. Writers and artists explored ambiguity, multiplicity, and the limits of perception. Philosophers debated the implications for determinism, free will, and the nature of existence. The dawn of quantum mechanics was thus not confined to laboratories. It reshaped human thought, inviting reflection on the relationship between observer and observed, knowledge and reality. Even as the quantum framework solidified, its mysteries remained. Entanglement and non-locality hinted at connections that defied classical intuition. Wave function collapse raised questions about measurement and consciousness. The universe revealed itself to be more complex, interconnected, and subtle than ever imagined. Each answer generated new questions, perpetuating a cycle of discovery that continues to this day. The dawn of quantum mechanics, far from a conclusion, became the foundation for further exploration into the heart of matter, energy, and the cosmos. Through all this, the human element persisted. The pioneers of quantum mechanics demonstrated that progress requires not only intellect but courage. Courage to abandon cherished assumptions, courage to confront paradox, and courage to trust in abstract reasoning where intuition fails. Their work illustrates the interplay between imagination and rigor, theory and experiment, human curiosity and the stubbornness of nature itself. The dawn of quantum mechanics was as much a human achievement as a scientific one, a testament to the capacity of the mind to perceive truths beyond immediate perception. The practical consequences of the theory are everywhere. Lasers, transistors, semiconductors, MRI machines, and quantum computing all rely on the principles discovered during this revolutionary period. Yet the philosophical and conceptual contributions are equally profound. Quantum mechanics reshaped the human understanding of reality, revealing a universe governed not by certainty alone but by a rich tapestry of probabilities, interactions, and hidden structures. It challenged assumptions, expanded imagination, and transformed both thought and technology. In the end, the dawn of quantum mechanics was not a single event, but a process, an unfolding revolution that reshaped science, philosophy, and human understanding. From Planck's first quanta to Schrödinger's wave functions, from Heisenberg's matrices to Dirac's relativistic formulations, the theory built a new vision of reality. It challenged classical certainty, revealed the probabilistic nature of existence, and opened pathways to technologies and insights that define the modern world. The quantum revolution demonstrated that reality is far more subtle, interconnected, and mysterious than classical physics could ever capture, and it marked a turning point in humanity's ongoing quest to understand the cosmos. By the mid-20th century, the abstract principles of quantum mechanics had moved from theoretical speculation to practical application, transforming both science and technology. The once mysterious behavior of atoms and subatomic particles could now be predicted with remarkable precision, opening doors to an unprecedented understanding of matter itself. Laboratories across the globe buzzed with activity as physicists devised experiments that made the invisible world tangible. Electron microscopes peered into the lattice of crystals, revealing the very arrangements of atoms. Spectroscopic techniques illuminated energy transitions, allowing scientists to map the internal landscapes of molecules. The atomic world, once purely theoretical, was now accessible, manipulable, and deeply understood in ways that had been unimaginable a few decades earlier. Quantum mechanics became the language through which these discoveries were made. The probabilistic nature of electron behavior, once a philosophical curiosity, provided the foundation for explaining chemical bonds, conductivity, magnetism, and even the behavior of light within materials. The Schrödinger equation described how wave functions evolved, revealing the likelihood of finding an electron in a particular state. Experiments confirmed these predictions with uncanny accuracy. The notion that electrons occupied discrete energy levels allowed chemists to understand why atoms bonded in specific ways, why molecules assumed particular geometries, and why materials exhibited their unique physical and chemical properties. The microscopic rules of quantum mechanics thus directly explain the macroscopic behavior of matter. Technological breakthroughs followed swiftly. The transistor, the fundamental building block of modern electronics, relied directly on the understanding of semiconductors, energy bands, and electron behavior predicted by quantum theory. Lasers, dependent on the controlled emission of photons from excited states, transformed communication, medicine, and industry. Even the understanding of nuclear energy, from both fission and fusion, depended on quantum principles governing particle interactions and energy levels. Quantum mechanics was no longer confined to blackboards and equations. It had become an engine of innovation, reshaping the modern world in ways visible in every corner of daily life. Beyond technology, quantum mechanics also revolutionized experimental physics. Particle accelerators allowed scientists to probe the innermost structures of matter, confirming the existence of protons, neutrons, and later, quarks and leptons. High-precision measurements tested the limits of quantum theory, revealing subtle phenomena such as the Lamb shift and quantum tunneling, which had no classical counterpart. The ability to manipulate and measure individual particles transformed science into an active exploration of the atomic landscape, where theoretical predictions could be tested with ever greater fidelity. The quantum world was no longer a distant abstraction. It was observable, measurable, and controllable. Quantum mechanics also unveiled the remarkable concept of superposition, where particles exist simultaneously in multiple states until observed. This principle underpins modern quantum technologies, from computing to encryption, and challenges traditional notions of reality. Entanglement, once an oddity described by Einstein as spooky, became a resource, enabling instantaneous correlations between distant particles that could be harnessed for secure communication and novel computational approaches. These phenomena demonstrated that quantum mechanics was not merely descriptive, it was predictive and utilitarian, offering new ways to manipulate and understand nature. At the atomic scale, quantum mechanics explained the periodicity of elements, the structure of molecules, and the behavior of light-matter interactions. Spectroscopy revealed the fingerprints of atoms, allowing scientists to identify elements, study their properties, and understand chemical reactions at a fundamental level. Quantum tunneling, where particles traverse energy barriers, seemingly impossible by classical rules, explained phenomena ranging from radioactive decay to modern electronic devices. Each experimental confirmation strengthened confidence in the theory, demonstrating its universal applicability and transformative power. The applications of quantum mechanics extended even further into chemistry and biology. Molecular orbital theory, derived from quantum principles, elucidated how atoms combine to form molecules with specific shapes and properties. Enzyme activity, photosynthesis, and even aspects of vision and smell could be explored using quantum models. The atomic and subatomic world was revealed as the foundation of life itself, a universe of rules, patterns, and interactions that govern not only the inanimate, but also the living. Quantum mechanics provided the key to understanding the machinery of existence at its most fundamental level. In the educational sphere, quantum mechanics reshaped curricula, laboratories, and research culture. Students and researchers learned to think probabilistically, to interpret abstract mathematical structures, and to design experiments that tested counterintuitive predictions. The tools of quantum theory became essential for exploring advanced physics, chemistry, and materials science. Its principles guided innovation in electronics, optics, and energy, demonstrating that knowledge of the atomic world could be translated directly into technological progress and practical applications. By the end of the 20th century, quantum mechanics had not only explained the structure of matter, but also transformed human capacity to control it. It enabled the construction of lasers that could cut and weld with precision, semiconductors that powered the digital age, and imaging technologies that revealed the inner workings of the body without invasive procedures. The insights of quantum theory had become embedded in everyday life, from the microchips in computers to the screens in smartphones. From MRI scans in hospitals to satellite communications, Quantum mechanics had moved from abstract thought to concrete reality, shaping civilization itself. The story of quantum mechanics in action is also a story of human ingenuity, creativity, and perseverance. The pioneers of the theory, from Planck and Einstein to Bohr, Schrödinger, Heisenberg, and Dirac, laid the groundwork, but it was the next generations of scientists who harnessed these ideas, translating theory into experimental exploration and technological innovation. Their work exemplified the interplay between imagination and rigor, showing that the universe's deepest secrets can be understood, controlled, and applied when humans are willing to challenge intuition and embrace the counterintuitive. Even as quantum mechanics matured, its mysteries persisted. Phenomena like entanglement, tunneling, and superposition continued to challenge classical intuition, inviting ever more sophisticated investigations. Quantum field theory and the Standard Model extended the principles to explain the interactions of fundamental particles, guiding the exploration of the subatomic world. The atomic landscape, once hidden, became a laboratory for discovering the universe's deepest rules, and the practical applications of this understanding continued to expand. In this way, quantum mechanics transformed not only science but also human capability. By unlocking the atomic world, it allowed control over matter and energy at the smallest scales. It illuminated the architecture of molecules, explained the stability of materials, and provided the tools to manipulate electrons and photons with unprecedented precision. Modern technology, medicine, and industry are built upon these principles. The atomic world, once invisible and mysterious, became a landscape where theory meets experiment, where knowledge translates into power, and where the counterintuitive becomes the practical. The story of quantum mechanics in action is, therefore, both scientific and human. It demonstrates the extraordinary capacity of the human mind to understand what cannot be seen, to predict what seems unpredictable, and to harness principles that defy intuition for practical ends. By confronting uncertainty and embracing probability, humanity unlocked the atomic world, transforming both knowledge and the world itself. Quantum mechanics revealed the deep structure of reality and provided the tools to interact with it in ways previously unimaginable, forever changing the way we live, work, and comprehend the universe around us. As the 20th century advanced, the insights of quantum mechanics transitioned from abstract theory to practical revolution, transforming not only science but the entire landscape of technology. What had once been a mathematical framework describing the strange and counterintuitive behavior of particles became a blueprint for innovation. Laboratories and research institutions around the world became engines of discovery, applying quantum principles to unlock the potential of the atomic and subatomic realms. Experiments that once seemed purely theoretical now yielded tangible results, revealing patterns and behaviors that could be harnessed to manipulate matter, energy, and information in unprecedented ways. Quantum mechanics reshaped the understanding of materials. The discrete energy levels of electrons, first theorized to explain atomic spectra, provided the foundation for solid-state physics. By understanding how electrons moved within crystals and semiconductors, scientists could engineer materials with precise electrical, magnetic, and optical properties. This understanding directly led to the development of transistors, semiconductors, and integrated circuits, the essential building blocks of modern electronics. The theory that had once existed only on blackboards now powered the digital age, enabling computers, smartphones, and the global communications networks that define contemporary life. Lasers, another product of quantum principles, demonstrated the power of controlling atomic and subatomic processes. By stimulating electrons to emit coherent photons, scientists could produce light that was not only intense and focused, but also extraordinarily precise in wavelength. Lasers became indispensable in medicine, industry, communications, and scientific research. From delicate eye surgeries to fiber optic data transmission, the ability to manipulate energy at the quantum level revolutionized countless aspects of daily life. Quantum mechanics had transformed from a set of equations describing probability waves into a practical tool for shaping the physical world. Nuclear energy, both fission and fusion, also relied fundamentally on quantum theory. Understanding the structure of nuclei, the interactions between protons and neutrons, and the energy levels within atoms enabled scientists to release energy on scales previously unimaginable. Quantum tunneling, a phenomenon once regarded as a theoretical curiosity, explained processes in both nuclear reactors and the sun's core, where particles traverse energy barriers that classical physics would deem impassable. The quantum revolution revealed that even the most massive energies in the universe obey the subtle rules of probability and wave function, connecting the microscopic and cosmic scales. The revolution extended into computing. The principles of superposition and entanglement offered the potential to process information in ways far beyond classical binary logic. Quantum bits, or qubits, could exist in multiple states simultaneously, performing computations at extraordinary speeds. Although practical quantum computers remain in development, the theoretical framework laid decades ago continues to guide this rapidly advancing field. Secure communication, optimization problems, and simulation of molecular systems are just some areas poised for transformation, demonstrating that the quantum revolution is both a historical achievement and a living, ongoing process. Even everyday technology owes its origins to quantum mechanics. Magnetic resonance imaging, the cornerstone of modern medical diagnostics, depends on the quantum behavior of nuclear spins. Photovoltaic cells, converting sunlight into electricity, rely on the quantized interaction of photons with electrons. LED lighting, high-precision clocks, and a myriad of electronic devices are all products of the theory that began as an exploration of atomic behavior. Quantum mechanics reshaped the relationship between human knowledge and practical capability, showing that understanding the rules of nature at its most fundamental level translates directly into transformative applications. The quantum revolution also reshaped experimental science. Particle accelerators, sophisticated detectors, and ultra-sensitive measurement tools allowed physicists to explore phenomena that were once beyond reach. The discovery of quarks, leptons, and bosons validated theoretical predictions while opening entirely new realms of inquiry. Experiments designed to test entanglement, superposition, and tunneling confirmed that the universe operates under principles radically different from classical intuition. Each confirmation reinforced the robustness of quantum mechanics, providing both a foundation for technology and a guide for further exploration. Philosophically, the quantum revolution altered how humanity perceives reality. The deterministic universe of classical physics gave way to a probabilistic one, where uncertainty is inherent and observation influences outcomes. Entanglement demonstrated that distant particles can remain correlated, suggesting a deeply interconnected universe. Superposition revealed that systems can exist in multiple states simultaneously until measured. These insights challenged assumptions about causality, locality, and objectivity, demonstrating that understanding the universe requires embracing its subtleties and complexities. Quantum mechanics revealed a reality that is participatory, relational, and astonishingly intricate. The revolution also accelerated interdisciplinary exploration. Chemistry, biology, and materials science all adopted quantum principles to explain phenomena previously mysterious. Chemical bonding, enzyme activity, photosynthesis, and molecular structure all became understandable through the lens of wave functions, probability distributions, and energy quantization. The quantum revolution illuminated the architecture of life itself, demonstrating that the same principles governing electrons and photons also govern the molecules that sustain organisms. Nature, once opaque and fragmented, became comprehensible as a unified system governed by the laws of probability and quantum interactions. Education and research adapted to the revolution as well. Universities established programs dedicated to quantum theory, experimental techniques, and applied technologies. Students learned to think probabilistically, to interpret abstract mathematical structures, and to design experiments capable of testing counterintuitive predictions. Laboratories became hubs of innovation, blending theoretical insight with practical application. The quantum revolution reshaped the culture of science, creating an environment in which imagination, rigor, and technical skill intersect to advance understanding and technological capability. By the latter half of the 20th century, the impact of the quantum revolution was undeniable. The digital age, modern communications, medical diagnostics, energy production, and advanced materials all trace their origins to principles first articulated in the early decades of quantum theory. The revolution demonstrated that deep understanding of fundamental laws allows humanity to transform the world, turning abstract knowledge into concrete power. At the same time, it preserved a sense of mystery, revealing a universe far more subtle, interconnected, and complex than classical intuition could ever predict. The human story of the quantum revolution is one of curiosity, persistence, and imagination. The pioneers who first explored atomic behavior, wave-particle duality, and uncertainty laid the groundwork. Subsequent generations harnessed these insights, translating theory into experiment and application. Their work demonstrates that progress depends not only on intellect, but on creativity, courage, and the willingness to confront paradox. The revolution is as much a testament to human ingenuity as it is to the elegance of nature's underlying rules. The quantum revolution also continues to inspire. Researchers push the boundaries of quantum computing, quantum communication, and nanotechnology, applying the same principles that once explained atomic spectra to create technologies that redefine possibility. Each new discovery, each application, is a continuation of the legacy begun by the earliest quantum theorists. The revolution is ongoing, demonstrating that understanding the microscopic world yields insights, capabilities, and innovations that extend far beyond the laboratory. Through the quantum revolution, humanity has learned to observe, predict, and manipulate the world at scales that were once invisible and inaccessible. It has revealed that reality is probabilistic, interconnected, and richly structured, governed by principles that challenge intuition but yield extraordinary predictive power. From the devices in our hands to the energy that powers our world, from the molecular machines within our bodies to the particles in the farthest reaches of the cosmos, the impact of the quantum revolution is pervasive, profound, and enduring. The story of the quantum revolution is, therefore, both scientific and human. It illustrates the capacity of the human mind to perceive hidden realities, to translate abstract understanding into practical innovation, and to embrace the counterintuitive in the pursuit of knowledge. The revolution transformed science, technology, and society, revealing a universe of possibilities and fundamentally reshaping humanity's relationship with the natural world. Quantum mechanics moved from theoretical curiosity to technological cornerstone, demonstrating that understanding the rules of the atomic world allows us not only to comprehend reality, but to shape it in ways that were once unimaginable. By the mid-20th century, the atom, once thought indivisible and simple, had been profoundly redefined. The classical picture of a tiny, solid nucleus, surrounded by orbiting electrons, no longer sufficed to explain the wealth of experimental data. Quantum mechanics had revealed that atoms were not static billiard balls, but dynamic, probabilistic systems. Electrons were not mere particles traveling in fixed orbits. They existed as waves, forming clouds of probability that could only be described statistically. The atom became a complex landscape, a universe unto itself, governed by principles that defied intuition yet provided extraordinary predictive power. The early experiments that revealed the discrete spectra of hydrogen and other elements forced scientists to rethink atomic structure. Classical physics could not explain why atoms emitted light at only specific wavelengths. Quantum theory provided the answer. Electrons occupy quantized energy levels, and light is emitted or absorbed only when electrons transition between these levels. This concept, once abstract, became foundational, explaining the colors of fireworks, the emission of neon signs, and the intricate spectral fingerprints of stars. It was as if the atom had a hidden architecture, one that could be read and understood through the lens of quantum mechanics. Further studies revealed that electron behavior was governed not by deterministic paths, but by probability distributions. Schrödinger's wave equation allowed scientists to visualize these distributions as orbitals, regions where electrons were likely to be found. These orbitals were not uniform. Their shapes reflected the symmetry and energy of the system, explaining chemical bonding, molecular geometry, and the reactivity of elements. The atom was no longer a simple structure. It was a dynamic, interacting system, a foundation for understanding matter at all scales. The probabilistic nature of electrons also gave rise to the concept of spin, an intrinsic property that had no classical analog. Spin explained the arrangement of electrons in shells and subshells, the Pauli exclusion principle, and the magnetic properties of materials. It revealed that even within the smallest components of matter, there existed rules of organization, hierarchy, and interaction. These discoveries transformed chemistry and solid-state physics, allowing scientists to design new materials, understand conductivity, magnetism, and superconductivity, and predict the behavior of complex molecular systems. The atom, reimagined through quantum mechanics, was also a source of technological innovation. Understanding electron energy levels and transitions enabled the development of lasers, semiconductors, and magnetic resonance imaging. Quantum tunneling explained how electrons could pass through energy barriers, leading to advances in electronics, including the design of diodes and transistors. The abstract principles governing the atomic world were no longer confined to theoretical physics. They were actively shaping technology, medicine, and industry. The once hidden rules of matter became tools for human ingenuity. Experiments probing the atom continued to uncover surprises. The Stern-Gerlach experiment demonstrated the quantization of angular momentum, revealing that particles exist in discrete states rather than a continuous spectrum. Electron diffraction experiments confirmed the wave-like behavior of matter, showing interference patterns previously thought impossible for particles. These results reinforced the notion that the atom was not a simple object but a complex system governed by probabilistic laws, symmetry, and wave-particle duality. Each experiment provided a glimpse into the underlying order and strangeness of the microscopic world. The reimagined atom also illuminated the connection between physics and chemistry. Quantum mechanics explained why elements have specific chemical properties, why molecules form particular shapes, and why reactions proceed in predictable ways. Molecular orbital theory, derived from atomic wave functions, allowed chemists to understand bonding, reactivity, and spectroscopy with unprecedented accuracy. The atomic world became a canvas upon which both natural laws and human creativity could act, revealing the interconnectedness of matter, energy, and information. Beyond individual atoms, quantum mechanics reshaped understanding of solids, liquids, and gases. Band theory explained electrical conductivity and semiconductivity, while the behavior of electrons in lattices revealed the principles behind superconductors and magnets. Quantum mechanics provided a unified framework for understanding how microscopic rules translate into macroscopic properties. The atom was no longer isolated. It was the building block of matter, a system whose interactions determined the properties of materials and the behavior of the world at large. The philosophical implications were profound. The atom's behavior challenged classical determinism and introduced inherent uncertainty. Heisenberg's uncertainty principle showed that certain properties, such as position and momentum, could never be precisely known simultaneously. The act of measurement itself influenced the system being observed. The universe, once thought predictable and fixed, was probabilistic, interconnected, and dynamic at its core. Understanding the atom required embracing a reality in which certainty was limited and observation-shaped existence. The reimagined atom also demonstrated the unity of scientific disciplines. Physics, chemistry, and materials science converged through the principles of quantum mechanics. Insights into atomic structure informed chemical synthesis, the design of new materials, and the development of electronics and photonics. The atom became a bridge between theory and application, linking fundamental understanding to technological innovation. This integration exemplified the power of quantum mechanics to illuminate nature across scales, from the subatomic to the macroscopic. Educationally, the new understanding of the atom transformed teaching and research. Students learned to think probabilistically, to visualize wave functions, and to use mathematical models to predict chemical and physical behavior. Laboratories provided hands-on experience with quantum phenomena, from spectroscopy to diffraction experiments, linking abstract theory with tangible observation. The atom became not just a concept but a laboratory for exploration, a foundation for inquiry that continues to shape generations of scientists. Technological applications multiplied, demonstrating the practical power of the reimagined atom. Lasers, transistors, semiconductors, MRI machines, and LEDs all relied on principles discovered through the study of atomic behavior. Quantum tunneling enabled advances in electronics, while understanding spin and magnetic properties facilitated data storage technologies. The atom, once invisible and mysterious, had become a playground for innovation, a realm in which theory and experiment combined to create tools that define modern life. The human story behind the reimagined atom is also remarkable. The pioneers who challenged classical assumptions, questioned intuition, and embraced abstract mathematics demonstrated extraordinary vision and courage. Planck, Einstein, Bohr, Heisenberg, Schrödinger, and countless others laid the groundwork, but it was subsequent generations of scientists who transformed theory into discovery and application. The atom became a symbol of human ingenuity, a testament to the capacity to perceive, understand, and manipulate the fundamental structures of reality. In conclusion, the atom reimagined by quantum mechanics is a universe in miniature. Its structure, behavior, and interactions reveal the underlying rules of matter, bridging the gap between abstract theory and practical application. It illuminates the connections between physics, chemistry, biology, and technology, showing that understanding the smallest constituents of matter enables control over the largest. Quantum mechanics transformed the atom from a mysterious particle into a rich, dynamic, and manipulable system, forever changing the way humanity understands the building blocks of nature and the possibilities they offer for discovery, innovation, and insight. As the 20th century drew to a close, the journey of quantum mechanics extended far beyond the study of individual atoms and subatomic particles. The principles that once described electrons and photons now became the foundation for exploring the universe at all scales, from the tiniest quarks to the vast reaches of cosmology. Quantum mechanics, initially perceived as a strange and abstract theory, had evolved into a central framework for understanding reality, offering both profound insights into the natural world and the tools to manipulate it in ways previously unimaginable. The applications of quantum theory began to permeate every field of science. In materials science, understanding atomic and electronic structure enabled the creation of novel materials with properties engineered at the microscopic level. Superconductors carried electricity without resistance, revolutionizing power systems and magnetic technologies. Nanotechnology, which manipulates matter at the scale of individual atoms, became possible because the rules governing atomic behavior were now comprehensively understood. Quantum mechanics allowed scientists to predict and control phenomena that were once thought random or inaccessible, opening the door to innovations in energy, computing, medicine, and manufacturing. Quantum computing emerged as one of the most promising frontiers. Unlike classical computers, which process information in binary states, quantum computers leverage the principles of superposition and entanglement. Qubits, existing simultaneously in multiple states, can perform complex calculations at speeds unthinkable for traditional machines. This technology holds the potential to revolutionize fields ranging from cryptography and artificial intelligence to climate modeling and drug discovery. What began as theoretical speculation decades earlier is now shaping the future, demonstrating that understanding the microscopic rules of nature can yield transformative power at a macroscopic scale. Quantum communication also illustrated the practical power of entanglement. By linking particles over vast distances, scientists could achieve secure transmission of information that cannot be intercepted without detection. This concept, once dismissed as purely theoretical, has been implemented in experimental networks, and it promises to redefine cybersecurity, ensuring privacy and security in ways that classical systems cannot match. The principles that governed electrons and photons now form the basis of entirely new technologies, showing that the quantum revolution continues to influence daily life in tangible ways. At the same time, quantum mechanics continues to challenge our understanding of reality. Entanglement defies classical intuition, suggesting a universe in which distant objects remain fundamentally interconnected. The superposition of states raises questions about observation, measurement, and the nature of existence. These phenomena are not only technical challenges for physicists, they are conceptual puzzles that force a reconsideration of causality, determinism, and the limits of human knowledge. Quantum mechanics demonstrates that reality is far more complex, subtle, and interconnected than everyday experience might suggest. Cosmology and fundamental physics increasingly rely on quantum principles. The behavior of the early universe, the formation of particles after the Big Bang, and the properties of black holes all intersect with quantum theory. Quantum field theory, unifying quantum mechanics with special relativity, provides a framework for understanding fundamental forces and particles. Ongoing research seeks to reconcile quantum mechanics with gravity, aiming for a unified theory that could explain phenomena from subatomic scales to galactic structures. Quantum mechanics is not only a tool for understanding the small, it is a guide to understanding the universe itself. In biology and chemistry, quantum principles reveal the intricate mechanisms that sustain life. Photosynthesis, enzyme reactions, and even the processes of vision and smell involve quantum effects, such as tunneling and coherence. The study of these phenomena has given rise to quantum biology, an emerging field exploring how quantum mechanics shapes living systems. Molecular simulations, powered by quantum calculations, enable the design of drugs, the modeling of complex reactions, and the creation of synthetic molecules with desired properties. By revealing the rules governing atoms and electrons, quantum mechanics has become essential for understanding and manipulating life at its most fundamental level. The philosophical implications of quantum mechanics remain profound. The universe appears probabilistic, interconnected, and participatory. Observations do not merely record reality, they influence it. Classical determinism gives way to a probabilistic tapestry in which uncertainty and correlation define the structure of existence. These insights challenge long-held assumptions about objectivity, causality, and the independence of distant systems. The study of quantum mechanics reveals a cosmos in which knowledge, observation, and the fabric of reality are deeply intertwined, suggesting that the universe is both stranger and more elegant than previously imagined. Education and research continue to adapt to these advances. Universities and laboratories train scientists to think probabilistically, to use abstract mathematical frameworks, and to design experiments that probe the limits of the quantum world. Students explore quantum phenomena, ranging from atomic orbitals to particle collisions, learning to navigate a universe where classical intuition often fails. The tools and concepts of quantum mechanics are now central to scientific literacy, equipping new generations to advance both theoretical understanding and practical application. Technological innovations derived from quantum mechanics continue to accelerate. Quantum sensors measure gravitational waves, magnetic fields, and time with unprecedented precision. Quantum dots and nanostructures enable advanced imaging, energy harvesting, and electronics. Quantum-enhanced materials promise more efficient solar cells, batteries, and superconductors. Each application demonstrates that the principles discovered in the atomic and subatomic realm can be harnessed to transform the macroscopic world, linking fundamental science to the everyday technologies that shape modern life. The human story of this seventh keynote is one of curiosity, perseverance, and imagination. The pioneers who first explored quantum phenomena laid a foundation of bold ideas, abstract mathematics, and rigorous experimentation. Subsequent generations took these concepts further, transforming theory into technology and philosophy into practical innovation. The quantum revolution illustrates the extraordinary capacity of humans to perceive, understand, and manipulate the natural world, even when it operates according to rules that defy intuition and everyday experience. In conclusion, the journey beyond the atom demonstrates that quantum mechanics is not merely a historical curiosity, but a living, evolving framework that continues to shape science, technology, and human understanding. From computing and communication to medicine, energy, and fundamental physics, quantum principles guide exploration and innovation. They reveal a universe of complexity, interconnectedness, and possibility, showing that the microscopic rules governing atoms and particles provide insights into phenomena ranging from the smallest biological systems to the largest cosmic structures. The quantum revolution is ongoing, promising discoveries and technologies that will continue to transform the world, redefine human knowledge, and illuminate the fundamental nature of reality itself.